work and energy, go and have a recap of what you learned before, and then teaching you the new knowledge. So we already know that work, meaning that to do something, to get something done. So in this example, just to show you what's the definition of work, I drew a car. And this car wants to move in this direction. So it wants to move to the right. Now, there are different people that are helping us. One is a person with a force of 40 Newton pushing forward. We have another person with a force of 100 Newton with the angle of 45 degrees. Force F3 is 100 Newton and force F4 is 50 Newton. So what I want to do, I would like to calculate how much the work from each of these forces would be. Now, by default, by just looking at this picture, who is the most efficient person? So if we just look into this picture, we would say, oh my God, F1 is just doing the work. The rest of them are like F3 creates zero work. Because if you push to the side, the car won't move. Even if the car moves, it doesn't move in the direction that you want. Now, how about force F4? It's actually pushing backward. Now, that's not the work you want, so that's what we call it a negative work. A negative work is happening when the direction of force and the direction of the displacement are opposite of each other, or distance, or whatever we call it, displacement or distance, they are opposite of each other. Now, I want to calculate for every one of those. We already know that work is equal to force times distance, or force times displacement. Now, in this example, if I have a displacement of 20 meters, I want to find the work from force F1, F2, F3, and F4. So by default, work from a force, we can say work from a force is equal to force times distance. Now, we already know that this is not completely clear. How about force F2? It has an angle. So it's force times distance times cosine of theta. Now, cosine was you already know how you calculate cosine, and then you have it in your calculator. You can actually simply calculate that. Now, for force F1, the angle between distance and force is simply 0 degrees. And then for force F2, the angle is 45 degrees. For force F3, the angle is 90 degrees. And for force F4, the angle is 180 degrees. So now I know that theta 1 is equal to 0. Theta for the force 2 is equal to 45 degrees. Theta for the force 3 is 90 degrees. And then theta for the force 4 is equal to 180 degrees. Now, if I want to calculate the force, what I could do actually, I already know the force for each of them. I know that F1 is equal to 40. F2 is equal to 100. F3 is equal to 100 again. And F4 is equal to 50. Now, distance is the same for all of them. So I can say work from force 1, W1, is equal to F1. How much the F1 is? Force 1 is 40. So it will be 40 times 20 times cosine of 0 degrees, which will be simply 80 joule. You can do the calculation for W2, which is from the second one. It's going to be equal to 100 times 20 times, so I have 100 times 20. So far I have 2000. Sorry, down here it was 20 and this was 800 joule. Now I have 100 times 20 times cosine of 45 degrees. Now if you do this calculation, the answer will be 1410. I'm just guessing. Joule. Now if I do it for the third force, W3 is going to be equal to the value for, I guess I I'm doing good. So for the third one, the force is 100, the distance is 20, and then the cosine of 90 degrees, which will make a 0 work. Then W4 is equal to 50, distance is 20, cosine 180, which will make a negative work of minus 1000. So if you add all this stuff together, you will actually find the net work done by these four forces. But I'm not intended to do that, but that's how you can do that. So the second work is work from gravity. We already know that gravity is a force, and then the force of gravity is actually mg. The direction of g, which is the gravity, is always down. So the direction of mg is actually going down. Now, if we take a block of, for instance, 5 kilogram, and we move this block for 2 meters up, the work that we generate would be equal to, now, 5 kilogram. So 5 kilogram is the mass, then you have to multiply it by g, and then we already know the value of g is 9.8. In this case, the work that you are doing is negative, because your displacement is up, but the mg is down. You see, displacement is this way, mg is this way. Now, the distance is this way, mg is this way, so this will create a negative work. So your answer will be equal to minus 5 times 9.81 times 2. Now, the reason is minus because of their opposite direction. So this time you have to actually give work, right? Whenever we give work to something, meaning that at the end, we're going to get a negative types of work. Now, in the second system, it actually generates work for us. Now, if you have 5 kilogram and this thing coming down for 2 meters, then in this time, we have the displacement this way, and then we have the mg this way too. So they are on the same direction. The theta is going to be 0 degrees. Then you can actually calculate how much the work for that would be. So you're going to get a positive work is equal to 5 times 9.81 times 2. Now in this case, in the first case down here, the work that you will be doing would be equal to 98.1 minus, and down here will be times the distance of 2 will be 98.1 positive work. Work from a spring. So if you have a spring and then you're stretching the spring or compressing the spring, in both cases you would have work. So now the work from a spring is half of K. So this K stands for stiffness or spring constant. And then this usually has a unit of Newton per meter. So the unit of that actually is force per distance. Now, in order to calculate, like for instance, in this case, assume that I'm getting this spring and I'm stretch it for delta x of 0.5 meter. The value for K is given to me as 100 Newton per meter. So this means that if I apply 100 Newton to this spring, it will become elongated for 1 meter. So every meter needs 100 Newton to become elongated. This is how stiff that spring is. In order to calculate work from a spring, I can say in this example, if I have this number, I can say work from a spring is equal to half of K, which is 100, and I have delta x 0.5 to the power of 2. The answer for this is equal to, so this will be 50, down here I'll have 0.25. The answer is 12.5 joule. And we already know that the unit for work is joule. The next lecture that I like to talk about is principle of work and energy. So what does principle of work and energy means? Meaning that, like for instance, if you drive your car, what you put in your car is gasoline, which is energy, right? And then once you drive your car, it gives you work. So it displaces you from place 1 to place 2. And we already know that from gasoline, not all of it comes to work. We have lots in the system. We have heat that goes outside. Inside the car, we have friction. But again, overall, out of the energy in the gasoline, you get 20 to 30% coming to work. The rest of them are going actually to different types of work. It goes to work for friction, or just simply get lost as energy. But what we want to talk about, we want to say that energy can be converted to work, and work can be converted to energy. So in the second example that I draw here, this is actually a hydro turbine, or a turbine where we get the hydro, we get the water comes to a flywheel, look like a turbine, then through that flywheel we produce energy, and then you use that energy at your home, right? Now in this case, what you do, you have the work from the rotation of this flywheel converted to electricity, which is energy that you use at home. Now we want to formulate that in physics. So what do we mean in physics? In physics, we say that work, so this is actually principle of work and energy. Work is equal to change in kinetics energy. Now, kinetic energy calls delta KE, which is going to be equal to delta, which is final kinetic energy minus beginning kinetic energy. So the letter F stands for final, the letter I stands for initial. Now KE is, we already know that kinetic energy is half of mv square. Now how can I calculate work? We already know how to calculate work. Now if you know the work and you know the kinetic energy in one side, you can calculate the kinetic energy on the other side. Now in this principle, like for instance, if a car is moving, now if you increase the force, it speed up. So the kinetic energy, because you are giving work to the object, kinetic energy of it will increase. Now you can have examples where the kinetic energy could decrease, like due to friction, due to effects like that. Due to work from friction, kinetic energy can reduce. Or like any types of opposite motion of if you have an opposite force which create a negative work, then eventually you ended up at the situation where kinetic energy reduces. So in this example, I have a 1200 kilogram car. So the mass of this car is 1200 kilograms. So I have m is equal to 1200 kilogram, and then it's traveling with the speed of 10 meters per second. The driver pressed the gas, which generate a force of 2000 Newton on the tires. If the car moves for 100 meters, find the velocity of the car. So this is the car in the beginning. What we do, we press a force here, and that force is 2000 Newton, and the displacement of the car is for 100 meters. And I want to find what's going to be the second velocity of the car in this stage. Now, by just looking at this problem, you would notice that because you are applying a force which is in direction of the motion of the car, then your velocity will increase. Now, velocity will increase to a different value, which is going to be higher in this side. Now, how we do the calculation? So the work will be 2000 times 100. 2001 times 100 will be 200,000 of, so the work would be equal to 2000 times 20, which generate 2000 not times 20, because it traveled for a distance of 2000 times 100. The answer is 200,000 joule. Now, in the beginning, you were going with 10 meters per second. We want to know the velocity down here, how much the velocity in this location will be, V here. Now, kinetic energy final, we don't know. We know it's going to be half of m, V final to the power of 2 is equal to half of m is 1200 v final to the power of 2. Now if you simplify this will be 600 v final to the power of 2. Now kinetic energy in the beginning, initial, is half of mvi to the power of 2, which will be half of 1200 times the initial velocity, which is 10 to the power of 2. I can actually simplify the very last one. So I got 600 here times another 100. I'm going to get, so I have 600 times another 100 will be 60,000. Now let's solve it. Now we already know that work is equal to delta Ke, which is equal to Ke final minus Ke initial. So the amount of work that we have is 200,000 is equal to Ke final. Ke final we don't know. We just know Ke final is 600 Vf to the power of 2, and then your initial kinetic energy was 60,000. Now if I bring this one to the other side, I'm going to get Vf to the power of 2 is equal to, so this will be added because we become positive. So you're going to get 260,000 divided by 600. And then from there you can actually calculate how much Vf is. And we are sure the Vf is going to be much larger than the Va. So Vf is equal to 260,000 divided by 600. Now you can actually calculate the value for this and then find how much V final is. In the second problem, we have a 5 kilogram block. So actually I forgot to draw the picture. The picture is look like this. We have a spring and then this block is resting against the spring. So it's not actually attached to it. It's just resting. The question tells us that if we compress the spring, so this is shape 1, in shape 2, if I compress the spring for 0.2 meter, so delta x is equal to 0.2 meter. The question asks me, find the speed of the block after it's released. So I want to find how much the velocity of block would be once I release it. And how it works here. So we have a kinetic energy and we have a work. So we can say work is equal to delta Ke, which is Ke final minus Ke initial. So your initial velocity is 0 because it's simply resting, right? When we say resting, half of mvi is 0. Half of mvi to the power of 2 is 0. And then for final, we don't know, right? For final, it's going to be half of m, which is, let me just to write the equation, then I would calculate m v final to the power of 2. And then that's going to be half of, the value for m is 5 vf to the power of 2. Now, how much work are we do? Work is simply from a spring. We don't have any other work here. And work from a spring is half of K delta x to the power of 2. Let's solve it. So we have half of K to the power of delta x to the power of 2. And then the value for K is given as us to 100. Delta x is given as 0.2. Then I can actually start solving the problem. So I have half of 100 times 0.2 to the power of 2 is equal to half of 5 Vf to the power of 2 minus 0. So 0 is 0. Then from here I can actually calculate how much Vf is. So the half from both sides, you can cross them off. Then this 100, you can cross it off with 5, you get a 20 here. So your answer is Vf is equal to Vf to the power of 2 is equal to 20 into 0.2 to the power of 2. Now Vf to the power of 2 is equal to, this is going to be 0.04, and then times 20, the answer is 8. 8, and then Vf is equal to √8 meter per second. So thank you very much for listening this specific lecture. Then I'm going to have another lecture for this week too. That's about potential energy and kinetic energy. We're going to talk about conservation of energy. And thank you very much for listening to this lecture. I'm going to post the PDF of this file too, so you can actually look into how I solved the example